Okay, now we have this circuit. Now, what we did was we had this RC circuit, which we had discussed on Thursday, and now we added a resistor. Now, we more or less know how the system will behave. So without the resistor, we know that it was just an oscillating system. The current was changing from a maximum value to minus the maximum value. It was oscillating with an oscillation frequency given by this equation over here. Well, it just looked like a pendulum, an electronic pendulum, let's say. Now, when we add the resistor, we qualitatively know what there will be. We know that the energy, we will be losing energy. But energy loss just means that since the maximum energy is in both of them, E and B, well, the total energy is just constant, equal to the maximum values. It just means that the maximum Q0 and Q0 omega will just decrease in time. That's what the reduction in the energy means. So with time, this much energy and energy proportional to the current squared will be dissipated, and hence the charge in the capacitor will never reach its initial value. So it starts with some maximum value, then there will be some oscillation, and at the end of the first oscillation, the maximum charge in the capacitor will be smaller because some of the energy is lost. And in the one more cycle, it will get even smaller, etc. So this is qualitatively what we expect will happen. Now, quantitatively, now there are two things that change. First of all, the frequency. Remember, the frequency in the absence of the resistor was 1 over LC. But if you remember the RC circuits or RL circuits, what resistor does is it kind of prevents the increase of the current. It slows down the increase of the current or the change in the current. So if there is a resistor in the circuit, so this is the new frequency. It will be slower, well, mainly because the resistor will slow down the process a bit, so it will take a longer time to complete one full cycle. Well, that's why it is slower. Now, the charge as a function of time will also be similar, let's say Q0 cosine omega t plus some delta. This delta will be determined by the initial value, but this is just an oscillation up and down. There is also a damping, minus R over 2LT. Now, how do you get this equation? You just put this equation into our differential equation and you just verify that this is true. Next year, you will learn how to drive this equation. Well, it will not be so important for us, it will be more important for the time being just to understand what these are. So it's, again, we have an oscillation, but this oscillation is damped. Now, of course, we also have all these cases. Well, let's say if R is small, the resistor is small, then omega squared is positive, then this is what we will get. We will have an oscillating system, although the amplitude will be diminished. It might happen that R is very large. Let's see. R squared over 4L squared minus is smaller than 1 over LC. If this is smaller, then we know that omega squared is positive, as it should be. So this is the description we have. So the charge as a function of time, it will be oscillating up and down, and it will be damped. Now, it might be that R squared over 4L squared is larger than 1 over LC. Now, if this is true, R squared over 4L squared is larger than 1 over LC, omega squared is negative, so this solution doesn't really make too much sense. Now, the solution we have in this case is we don't have an oscillation, but we have an exponentially damped system. So it's mainly, now in this case, It is mainly we have a large resistor and let's say an L or C. So there won't be any oscillation. The system just loses all its energy before completing one full oscillation. Now this is underdamped. This is overdamped. And then we also have what we call the critically damped. This is equal to 1 over LC. Now, in this case, it almost makes a oscillation, but fails to do it. So this is what we have in that case. Now, in this one, in fact, I didn't draw it so precisely correct. Oops. Why not? So, for example, it depends on your initial conditions. What are your initial conditions? For example, if you just consider this as part of your system, part of this system, you first put the switch at this point, make sure that the capacitor is fully charged initially, and then you just move this circuit to the other position. If that is your T equal to 0, at that time your capacitor is charged, there is no current in your system. So the current will increase with time, the charge will decrease in time. So this is a system in which the current starts from 0 and keeps on increasing. Now, the more interesting example will be the driven RLC circuits. Now, where do you use such an RLC circuit? In real life? You probably don't use this circuit. But you do use the other RLC circuits with a power supply, AC source. Do you know any example of this one? Where do you use this? In everyday life? Where at home? Audio systems, in computers, in radios. A simple radio is nothing but this one. This is a simple radio. Now, we will study electromagnetic waves. But electromagnetic waves, for the time being, just know that they are just changing electric and magnetic fields. So when you have a changing electric and magnetic field, they will just cause the charges in this antenna to move up and down. And once they are moving up and down, that will create a time-dependent current. But if there's a time-dependent current here, it will induce an EMF over here. And that EMF will create some current running in the second loop, and this is your speaker. This is what you call this is our resistor, what we call in our circuits, what we show as a resistor can as well be a speaker. We are not specifying what it is. Here, this one provides, now due to the mutual inductance, there is both AC power EMF, an alternating EMF source, and an inductor over here. There is both the mutual inductance and also the self-inductance of this one. Both will play the game. Now, for this circuit, we can just take that circuit and model it. This is just a model of this part of the circuit, as we have an inductor, we have a capacitor, here we have a resistor. Let me also put some AC source over here. This is our AC source. This is just a simple model of this radio. Now, the AC source over here and the inductor in this radio is the same. This inductor here, due to its mutual inductance with the external solenoid, it creates this AC source, the EMF source. Now, let's study those circuits in more detail. This is epsilon 0 times, let's say this is cosine omega t. Now, without this AC source, we already know what the circuit equation was. If you remember, it's L d squared q by dt squared plus R dq by dt plus q over c. This was equal to 0 without this AC source, but now we have some source which we should add to this equation. Now, this is the equation that we need to solve now. Now, if we wait long enough, now you can just imagine this as a part of a circuit. If we wait long enough, the solution of this, the current in the circuit, will be nothing but Q of t. Well, it will just oscillate with the same frequency, omega. Let's say it is equal to Q0 cosine omega t plus delta. This is how Q will change. I of t will be, let's say, I0. Now let's say this is sine. This will be cosine omega t plus delta. And we already know that I0 is nothing but omega Q0. Now, this omega here is just this free parameter over here. We don't know what this power supply is. You can just set its frequency. Now, the question is, what should omega and Q0 be so that this function satisfies that equation over there? That is what we will try to solve. Now, we said that Q0, Q of t, is equal to Q0 sine omega t plus delta. What else do we know? dq by dt is Q0 omega cosine omega t plus delta, and d squared q by dt squared, this is equal to Q0 minus Q0 omega squared sine omega t plus delta. This is the equation. And if we just put this over here, we get minus Q0 L omega squared minus 1 over c sine omega t plus delta plus r omega Q0 cosine of the same thing. This should be equal to epsilon 0 cosine omega t. Now, I just put these equations over here. Now, in In your last experiment, if you remember, we were already discussing the impedance of such circuits. We had the inductive impedance, the capacitive impedance. If we just take out this one of these omega factors, now this is why you have that minus sign in between. If you look at the term with the capacitance, it is the second derivative, and term with the capacitor, now term with the inductance, it has this minus sign. Term with the capacitance, it doesn't have that minus sign. Now, of course, this is a solution. We have to solve that equation. Has to be valid at all times t, not just at one time t. At every time this has to be satisfied. That is why, although we seem to have a single equation, this equation is enough to determine we have two unknowns. One equation, two unknowns, but since this equation is satisfied at all times, it's more than enough to determine those unknowns. Now we will use a different trick rather than trying to solve this equation directly. We will use the vectors. Now you see here I have three terms. Each one of them contains some sines or cosines. They have to be equated to some other term which also contains cosines. Now whenever you have these cosines and sines, you should always remember the vectors. Because if you imagine a vector, let's say this is some arbitrary vector. Let's say its length is epsilon 0. And this angle over here is omega t. Of course, with time, this angle will change. This whole graph will be rotating in time. But here I have some vector. And let's say this is the x, this is the y, or the horizontal component of this vector is nothing but epsilon 0 cosine omega t. It is this one. So this just tells me that I can think of this quantity as one of the components of a vector. It will simplify my life. Okay, this is the x component of a vector. So if, for example, if I can find three vectors whose x components are these expressions reflectively, and then I just convert this equation to a vector equation, to vector sum. Furthermore, you see, if you look at all these three equations, they all have the same angle, but some of them are sine, some of them are cosine. Sine and cosine, they just differ by 90 degrees. So these vectors, the vectors corresponding to these ones, they will be either in the same direction, in opposite direction, or at 90 degrees. Well, the vector corresponding to this one and this one, due to this minus sign, now this term and this term, due to this minus sign, they should be pointing in opposite directions. And furthermore, well, they are also the sign. They all have the same sign. The vector corresponding to this one, it has the cosine, but it has the cosine, so there's a 90 degrees between this vector, the vector corresponding to this one, and all the rest. Now, first of all, here we had this angle omega t. Here we have the angle omega t plus delta. So let me first write that vector. Here I have another vector. This angle over here is delta. So this, if you look at this term, r times dq by dt, or r times I, it is q0 omega times cosine omega t plus delta. So let me erase this one. That vector has length epsilon 0. This vector has length I0. And I0 is q0 omega. So I will rather stick with I0. So the x component of this I0 vector is nothing but this Q0 omega cosine omega t plus delta. Okay, so I already identified this vector. Now let's look at this one. Now I can write that one as, this is equal to I0 over omega times cosine of pi over 2 minus omega t plus delta. Okay, Q of t was I0 over omega cosine of pi over 2 minus omega t plus delta, but this is also the same thing as I0 over omega cosine omega t plus delta minus pi over 2. Cosine of an angle is equal to cosine of minus that angle. So the angle, whatever this corresponds, whichever vector this corresponds to, it makes a 90 degrees with omega t plus delta. The angle it makes with the horizontal axis is reduced by pi over 2. By the way, here I have, this is r times I0. I have this term, r times I0. Now I'm looking at this term Q over C, but we just said that Q over C, the vector corresponding to Q over C makes 90 degrees less. So this is the vector corresponding to Q over C. It has a magnitude Q0 over C. Now let me, okay, this is 90 degrees. So if I take the x component of this vector, it gives me this term over here, this Q over C. If I take the x component of this vector, it makes an angle omega t plus delta with the horizontal. Its length is r times I0. It gives me this quantity over here. Now I need to find a vector whose horizontal component is equal to this one, so that I will have found 3 vectors, each corresponding to these ones. The x component of each one of those vectors will correspond to these terms. I have the fourth vector whose x component corresponds to this one. Now if this satisfies vectorially, it is also satisfied for the x components, and I have the solution. That's the strategy. Now the last one is this one over here. So it is L that term is L d squared q by dt squared, which is L over omega. No, L minus L omega Q0 I0 sine omega t plus delta. I will do a similar trick. I will try to write this as the cosine of some angle. This is equal to L omega I0 cosine of omega t plus delta plus pi over 2. I just again use the properties of the trigonometric functions. I know that cosine of theta plus pi over 2 is equal to minus sine of theta. Again, the vector that corresponds to this term, it makes an angle with the horizontal that is 90 degrees more than omega t plus delta. So this is the vector that makes an angle omega t plus delta with the horizontal. If we add 90 degrees to it, we will be here. and the length of that vector is L omega I0. And this is I0 over omega C. Now I have 4 vectors here, and those 4 vectors are chosen such that the x components of all of these vectors correspond to the terms over here. So if the sum of those, the 3 orange vectors, okay. Now the vectors in orange, each one of them correspond to one term on the left-hand side, and the vector in black corresponds to the x component corresponds to the right-hand side. So if the sum of these 3 vectors is equal to the 4th vector, the same holds for the x components. Now, of course, the figure over here is not up to scale, so let me just correct it a bit. This shouldn't be so big. It has to come somewhere up to here. So here I should sum these two vectors. It should give me a vector. It should give me this vector, the sum of these two. And this should, here I have a right triangle. Now let's see, the length of this side, the length is equal to omega L minus 1 over omega C times I0. I know that this vector has length omega L I0. This vector has length 1 over omega C I0. They are pointing in opposite direction. So if I just sum them up, the resultant vector will have this length. Now this length, we already said that it is nothing but I0. This vector has length I0 times R. And so here I have a right triangle. The perpendicular sides, one has length I0R. The other length has sides omega L minus 1 over omega C I0. And the sum should have length epsilon 0 squared. Okay, in the sketch at least, it is this one. For this sketch, yes. Now we can also determine the angle delta from the same triangle. Okay, so this is one equation we have. If you look at tangent of this angle delta, it is just this side divided by this side from the right triangle again. So tangent delta is equal to this side with this minus sign 1 over omega C minus omega L divided by R. So if you remember our initial guess for the solution, Q was I0 over omega cosine omega t plus delta. No, sine omega t plus delta. this was our initial guess. We had two unknowns. We didn't know what I0 is, we didn't know what delta is. And now we have determined both I0, no, the next one. We have determined I0 from this equation, and we have determined delta from the other one. Okay, if you don't remember how we derived it, it's not that important, but the results will be important, and how we can make use of these results. Now, first of all, let's look at this one. Well, let's just look at this one. Now, that equation we can write as I0 is equal to, or I0 times square root of R squared plus 1 over omega C minus omega L squared. This is equal to epsilon 0. This is what we call impedance. Does it make any difference? Okay. So it's the same thing. So what does if the impedance is not equal to R, there's at least one thing we know. This delta is non-zero. So what does it mean to have delta non-zero? Well, if delta is not zero, when the power supply provides the highest potential difference, the current will not be at its maximum. They differ. The maximum of the power supply and the maximum of the current, they will differ. Now, the other thing that will be important is when you create your circuit, there will be an adjusting knob for your power supply, let's say. So you can change omega, but once you prepare your circuit, L is fixed, C is fixed, R is fixed. And if you would plot this I0 as a function of the frequency that you provide, you see, suppose you just keep epsilon 0 constant, it is constant. You are just playing with omega, with the frequency. Now, if you change omega, there will be a value of omega in which this quantity is 0. This is equal to 0. And this so-called resonant frequency is 1 over square root of LC. Now, but this is nothing but the frequency at which if we only had an LC circuit, an inductor and a capacitor, that circuit will oscillate with this frequency. It's kind of the natural frequency of oscillation. Now, if you force a system at its natural frequency, that is what we call the resonance phenomena. So what happens in resonance? Okay, in this case, I becomes maximum, but you already have a resonance phenomena in your everyday life. Or especially when you were a small kid, you were making use of this resonance phenomena in the swings. Yes, you remember your mechanics course. You see, what do you do in the swings? The swing as a pendulum, it has its own natural frequency of oscillation. So when you want, if you want to swing on your own without getting any help, you just swing back and forth, and you just adjust your swinging back and forth. You lean forward, you lean backward, and you adjust your frequency to the natural frequency of the oscillator. If you do that, the amplitude of oscillation increases. With a very small influence, I mean, the fact that you are leaning back and forth, it has a very small effect, but nevertheless, it can create a huge amplitude for your oscillation. The same thing happens over here. If you force the charges in a circuit to oscillate at their natural frequency, the amplitude will increase in time. And the maximum amplitude that you will reach, okay, if you will have such a dependence. This is where you have the omega R. This is your resonance frequency. And the maximum value will be nothing but epsilon 0 over r. Now, at the natural frequency, well, this just cancels itself. 1 over omega c and omega l, they are equal. Furthermore, since they are equal, delta is itself 0. So it just behaves as if it's an ordinary resistive circuit without the inductors and the capacitance. They both become a maximum at the same time, a minimum at the same time. Now let's go back to our circuit, our radio. Okay, this is of course one way of achieving the resonance, achieving the resonance and building up a large current. You can change the frequency. Now when you use the radios, we had this simple circuit of our radio. This is our antenna. It will be connected to an inductor. There will be a capacitor, which is grounded. And here you have your second circuit. Okay, and this is your speaker. Now we will see that electromagnetic waves over here, they don't come at single frequency. All the frequencies exist over here. And all those frequencies will try to build up a current in your circuit at their own characteristic frequency. And the net current in your circuit will be nothing but sum of, let's say, I omega cosine omega t plus delta. Now for each frequency in the electromagnetic wave, there will be some current induced in your circuit, and the net current running in your circuit will be nothing but the superposition of them. Of course, for each frequency you have a different amplitude for the current. Now what you want to do is when you take a radio, you just adjust the tune to the frequency. You have the Have you ever done that? Okay, classical radios, not the internet radios. There's a knob over there, you just change it so that you try to pick up a given frequency. Now what you are actually doing, remember the resonance frequency was given by 1 over LC. Now when you are changing that knob, what you are doing is you are changing C. And well, changing inductance is not that easy, so you just keep the inductance fixed, but you just change the capacitance of the capacitor. You change the capacitance, so you are changing the resonance frequency. So if when you are changing the resonance frequency, now in the sum there are all frequencies available. But you know that I of omega r is the largest one. It has the largest amplitude. Now, of course, there will be some fuzziness, but the maximum frequency, the maximum contribution to this sum will be from the frequency that has the resonance frequency. So by essentially you are just picking up one frequency in all these electromagnetic waves that are reaching your antenna. And that should be the frequency of the radio station that you would like to listen to. So your transmitter, the radio transmitter, we will be studying the simple ideas about the radio transmitters on Thursday and next Thursday. So they broadcast their signals at a given frequency or close to a given frequency, let's say. And you just adjust your receiver so that your receiver will also have a resonance frequency right at that broadcast frequency. And once that is satisfied, the current running in your circuit will only be sensitive to that resonance frequency. And so your speaker, from the speaker, you will just hear the signal from the radio station that you would like to listen to. Which one? Okay, now this is the radio. That is the speaker. So how does the speaker work? not exactly like this one. So what you have in the speaker, so you basically have a membrane. One thing you can do is you can just attach a magnet to the membrane. And here you have a coil. And at the end of this coil, you can, let's say, attach a speaker. And when you speak, this membrane will be vibrating. When sound waves come, this membrane will be vibrating back and forth, moving this magnet, and hence there will be a changing magnetic field in your coil, and you will get a current running through your speaker, and the speaker will create a sound. That's the basic idea of a speaker. Well, usually you don't put the magnet on the membrane, you put the coil on the membrane because it is lighter. Any other questions? Okay, this was kind of a fast introduction to the circuits. You will study circuits in more detail next year. Now, I will not continue with this circuits. We will, on Thursday, we will start with the Maxwell's equation, which I think are more important. Any questions on this one before we pass on? But of course, you need to be able to write down the equations governing the time dependence of the current for a given system. And you should remember that, for example, if you take a capacitor, what a capacitor does is, if the current is changing slowly, you see, let's look at this impedance equation. Suppose we have a circuit in which there is no inductance. No inductance. Now, if omega is huge, then it is as if the capacitor doesn't exist. Well, that is expected because if omega is huge, it means the current is oscillating rapidly, too fast, and during this oscillation, the capacitor doesn't have enough time to be charged. So the capacitor will always be neutral, almost neutral. So if the capacitor is not charged, then it just behaves as if it is an it's a closed circuit. It has no effect if omega is huge. Now, if omega is small, in that case, it will be fully charged and you will not be able to build a huge current in your circuit. The current will be very small. Now, for the inductance, if you don't have any capacitor in your circuit, forget this one. If you have an inductor, it is kind of the other way around. For small frequencies, the inductor will behave as if it doesn't exist, because inductor mainly tries to prevent the change. If omega is small, nothing is changing. So the inductor will just let small frequencies pass through, but it will not allow the large frequencies to pass through it, for the simple reason that for large frequencies, it will just try to prevent them. So that is, for example, one way. When you have the speaker systems at home, you will get if you get this large box, there are these small speakers and there's also the huge one. The huge one is mainly used to create the so-called the bus is used to create sound waves of very low wavelength. So here is this is the bus speaker. Here you will have a smaller one, and then you have your signal. This is your signal. From whichever source you get it, you can get it from some radio receiver, from some microphone. This is your time-dependent current. Now, what you would like to have is you would like to send the small frequencies to this big speaker. Now, if you want to send the small frequencies to the big speaker, just put a capacitor over there. No. Put a solenoid over there, an inductor. Because what an inductor does, it doesn't do anything at low frequencies, But at high frequencies, it prevents the high frequencies to pass through. And then you want to have the small frequencies go to the small speaker, but you don't want the large frequencies. So what you do is you want the large frequencies at the small speaker, not the low frequencies. So you attach it through a capacitor. Now what this will do is, in the signal, okay, this inductor will prevent high frequencies reaching your big speaker, and this capacitor here will prevent the high frequencies to reach the small speaker. No, the small frequencies to reach the small speaker. The small speaker will only receive low frequencies, and the big one will receive, no, the other way around. Okay, this is the high frequencies, and this is the low frequencies will reach here. So you have basically built up a frequency splitter. It just splits the frequencies into two. The high ones go here, the low ones go here. What would you like to do? You would like to send the low frequencies over here? Well, you see, the small objects have a high resonance frequency. That's why you would like to have high frequencies at small objects. You cannot create a very low frequency sound from a small speaker. That's the problem of small speakers. I mean, the sound, with small speakers, the sound is too, how do you say, thin, because it mainly contains high frequencies. It doesn't contain the low frequencies. Okay, there was a question somewhere over there. Okay. So let's see what happens over in this circuit. Now you create this vibration. The sound is mainly a collection of vibrations. So let's say that you cause this membrane to vibrate at a given frequency. Now you will be causing this membrane to vibrate in a superposition of all kinds of frequencies, but for the time being, let's just look at one frequency. You cause this to vibrate at one frequency. Well, it will create a flux in this solenoid with a time-dependent flux in the solenoid, and its time dependence will be governed by the same frequency. That means the current induced in this circuit will have the same frequency as the sound wave that hits this membrane. So the frequency of the sound will be equal to the frequency of the current running in this membrane. Now the speaker over here is in fact an identical system. Now here what you do is you get a solenoid, and here you have a membrane with a magnet. This is the membrane. So let's just imagine that a sound wave of a given frequency hit this membrane. It will start a current running in the circuit at the same frequency, but that means there will be a time-dependent magnetic field over here with the same frequency, but this magnetic field will be attracting this magnet over here. And that force will change with the same frequency. But this magnet is attached to the membrane. So this membrane will be vibrating at the same frequency as the sound wave that hit this membrane, which will cause vibrations in air which we interpret as sound. Any last questions? Okay, see you on Thursday.